Hello everybody. Today we're going to do a paperclip, a clip about a paper titled Is the Groundwater Reservoir Linear? Learning from Data in Hydrological Modeling. And this paper was authored by Paperclip Fenicia, Hubert Savenijen, Patrick Matren and Laurent Pfister, and it was published in Hydrology and Earth System Sciences. The paper comes up with a method to include low flows more explicitly in conceptual hydrological models, not just in calibration, but also in model conceptualization. And in the abstract, the authors argue that low flow periods in discharge simulations by conceptual models show a pretty poor performance. And they actually demonstrate that this is due to the fact that the model structure, basically meaning the conceptualization of the hydrological processes occurring in the catchment, are usually a priori defined rather than adjusted to the catchment's observed response, for instance in a hydrograph. Then they propose and demonstrate an iterative procedure to conceptualize these processes in a hydrological model and at the same time calibrating them to observations so as to achieve good performance during both low and high flows. And their experiments were conducted in catchments in Luxembourg, and these experiments demonstrate that in nearly all catchments they find that a linear reservoir, a linear relationship between reservoir storage and outflow from that reservoir best describes the observed groundwater behavior. Now this is all described in the first section, which is the abstract, the usual first section of a paper. Now on to the details. When we move to the introduction, we see on the top right an important note by the authors that stream flow during dry conditions is only sustained by groundwater. And in simple words, we can basically say that during these dry periods, it is not necessary to worry about all sorts of other processes. At least this is the hypothesis of the paper. Other processes that might influence discharge, simply because these are not active during these periods. And in particular, processes that relate more to the surface rather than the subsurface are relevant in periods where you don't have dry conditions. And then here in the middle, they basically make the point and the rationale behind the paper. And so although this behavior, the behavior of groundwater outflow, should be easy to recognize in observations, hydrological simulations often don't represent this because of inappropriate process representation. And inappropriate process representation, they mean by this the way processes work in reality is basically not well defined in the model structure. The second reason they put forward is unsuitable ways to calibrate the model, basically meaning tuning the parameters of the model to observations. Those are the two most important reasons treated here. Right, so let's move to page 2. I hope this works. Yes, it works. On page 2, they start to propose their iterative approach by which calibration of parameters and conceptualization of processes is performed in iteration. And they describe this more elaborately in the methods. So the low flow conditions where only the outflow from groundwater is active are specifically used in their method to estimate a limited set of groundwater related parameters within their model structure. And then they iteratively improve the groundwater generating component of the model. So basically changing the structure of the model, not just the parameter values. And then they mention nicely the earlier work in this field, but they also make clear that their methodology that is described here on the top right, that their methodology considers the entire rainfall runoff processes, not just low flows and not just high flows. Then they move on to the study area description. I'll be quite brief about this. Their description reveals that the catchment consists of a mixture of basically 3 geological landscapes: low permeable marl, described here, with high rainfall response and low flow dry weather periods. Then schists, which is described here, which is likely to sustain more discharge whilst having a pronounced response to rainfall still. And then finally sandstone, which is very interesting because it mainly sustains discharge through groundwater flow, which then surfaces as springs or at channel incisions. So all in all, the study areas represent a wide variety of catchment geology, which makes their sampling quite broad, I would say. A little bit about the data that they used. Well, we're actually in an area of the world, Luxembourg, which is not very data sparse. There's a lot of data, and for the present study, the authors have considered to use hourly data of rainfall, potential evaporation, and discharge. And they make a little statement here below as well that the data they use contains 3 years of information, and it covers the very large European summer drought of 2003, one of the hottest and driest ever recorded in Central Europe. Then moving on to the next section, the model description. The authors use the FLEX model structure, which is quite elaborately described here. FLEX model structure is a flexible model structure, and in this case, the flow processes and storage processes are represented by 4 reservoirs. I'll just turn to the next page to show you the graph of this. These are the 4 reservoirs: interception, an upper zone, a slow reservoir. This is the upper reservoir, a slow reservoir, and a fast reservoir. And from these 2 reservoirs, eventually flow comes out, which then contributes to stream flow at the end. Now they summarize the processes in this section as well, starting with the interception module. Interception represents the rainfall that is intercepted by leaves, vegetation, and the topsoil. And this is basically where the rainfall input goes into. And this reservoir is logically filled by rainfall first, and it cannot exceed some sort of maximum threshold. This is represented by the parameter Imax. This is a parameter which can be tuned to observations. So Imax basically represents the amount of water the leaves, vegetation, and topsoil can maximally hold. And this reservoir is emptied within the same time step as long as there is enough energy available for evaporation. And this amount of potential evaporation essentially is assumed to be proportional to the total potential evaporation used as input to the model as well. So it's a factor multiplied by the potential evaporation. All right, moving on to the unsaturated zone. That is this upper reservoir, conceptualized through this upper reservoir. This is a slightly more complex reservoir. The amount of rainfall that does not fit in the interception zone within a certain time step, so basically the amount of rainfall exceeding Imax, this is also called the effective rainfall. This amount moves towards this reservoir. You can see that by this arrow, but you also see that there is a split here between a certain amount going to the upper reservoir and a certain amount going to the fast reservoir. So the size of the portion going to the upper reservoir depends on how full that upper reservoir already is, for instance from previous time steps. We can see that in equation 2. This equation basically describes how that works. You can also see a plot of how that works for different values of the parameter beta in this function. And basically you can see if the reservoir is, if a larger portion of that reservoir is full, the more amount of water will go into the fast reservoir and the less goes into this upper reservoir. And this functional relationship describes that very nicely. It's a sort of a sigmoid functional form. So the remainder of the water will eventually run off, and fluxes moving out of this unsaturated zone are 2. There are 2 fluxes. The first is transpiration, which you can see in the arrow over here, and the next one is percolation, which is shown here by the symbol PS going into the slow reservoir. And so percolation essentially is the amount of water going through the soil towards the groundwater. The fuller the reservoir is relative to its capacity, the more percolation will occur, and there's an equation for that as well. It looks a little bit similar to the equation here, as it also uses SU over SFC, so the amount of water relative to the capacity of this reservoir, but then it's linearly multiplied by a coefficient, which is a calibration coefficient, again, P max. Now the transpiration works a bit in a similar way, but it is here bounded also by the amount of energy left over from the potential evaporation. Because remember, part of that potential evaporation, the amount of energy available for evaporation, essentially was already used by the interception reservoir, which we showed in the previous page. So you can see that here there is a limit. Where is it here? It is limited, it is bounded by the amount of potential transpiration, the amount of energy left over after energy consumed by interception. Finally, for this, there is also a parameter LP, which ensures that actual transpiration may already be maximized even below saturation level of the zone SU. You can see that occurring here. So LP is a calibration parameter between 0 and 1, theoretically. So then I think we have treated the upper reservoir, or the representing the unsaturated zone. And as we saw, water is transferred to the fast as well as the slow reservoir, here represented by FR and SR, through a linearly increasing transformation function. You can see that here with this triangle. And essentially this triangle is a convolution function that lags how water flows from one reservoir to the other. And the length of the convolution filter is determined by a parameter, the number of time steps essentially taken to lag the inflow into the next reservoir. And these basically control the lag time observed within the system, within data collected in the system through which the water moves. Then finally, the proportion RU of effective rainfall moves to the, sorry, I'm saying it wrong, to the fraction RF. So the amount of rainfall moving to the fast reservoir is indicated here in the graph. And from here, the water flows out according to a linear reservoir assumption. So essentially the fast reservoir is not going to be changed along the iterative framework the authors suggest, but they use a linear reservoir assumption here. And from here, a fast flow component flows out. And that is indicated here in this equation 6. The typical storage coefficient, the average time, residence time of water in the reservoir is Kf. Finally, we have the slow flow reservoir. This is a little bit more interesting. The authors here say in equation 7 that slow flow is a function of the storage in the upper reservoir, here indicated by the symbol SS. They don't give the functional relationship yet because, they, as we said earlier, they don't want to make any prior assumptions about that. And so Q is a function of storage, or QS is a function of storage, but how exactly, the authors make no prior assumptions about that. And how this is treated is described a little bit further onwards in the paper. So let's move to the next page. So then the authors describe the calibration procedure for low flows. And this is their first step towards full calibration of the model. And they repeat that in the first stage, they calibrate both the, at this moment, unknown functional relationship between low flows and storage in the slow reservoir, as well as the parameters of this functional relationships, along with all other parameters. And in the second step, they then recalibrate the high flow sensitive parameters to also describe the high flow. So this is sort of the summary of the method. Then they go into more detail. Of course, the procedure requires some sort of extraction of low flow periods. And they use a so-called master recession curve approach for this, which is described in section 4.1. They follow the procedure of Lamb and Bevan, which they mention here, and recession flow periods are basically with this method shifted in time such that their tail ends, so the last point in time of the recession, overlaps as much as possible with other recession flow periods considered. And this procedure is basically shown here in figure 4. Here you see all the recession periods in one graph, and all the tail ends of the recession periods have been overlapped with each other. So it's pretty easy to see here that the parts of the curve that still have to do with storm periods, which are these upgoing portions here of the hydrograph parts that they have extracted, these can very easily be distinguished from non-storm forced hydrograph parts, which are these lower parts that you see here at the bottom of the graph. The authors used a minimum recession period of 50 hours. And although it is not very clearly defined in the paper, I suspect that the authors used the complete receding periods in the full hydrographs of the 3-year periods that they used in the data to define recession limbs. They did not use any filters based on precipitation or potential evaporation or other signals that identify dry periods and distinguish it from wet periods. Now, the initial estimate of the storage-discharge relationship, let's look a little bit into that. I think that's on the next page. Yes, that is section 4.2. This is done through integration of the master recession curve in time, starting at the point of zero discharge. So they basically have to extrapolate the graph that we saw in the earlier page, and then moving backwards in time so that they can reconstruct the storage-discharge relationship. Now the assumption here is that the inflow of recharge during these recession periods, and this is basically the incoming flux into the slow flow reservoir, is negligible, and this is an assumption they test later in the paper. Now, through integration from the last moment in time upwards to the first moment in time, a storage-discharge relationship is reconstructed, for which an example is given in figure 5. So I need to go back to figure 5. Here you see this relationship. They use a trend line, that is the black line here, thinly indicated in the graph, up to an inflection point, which is here, to represent the storage-discharge relationship of this slow reservoir. And in the example they use, as you can see here, they use a second-order polynomial function for this. They do mention that many other relationships could have been used, power laws, exponential, and even linear, but in this case they selected a second-order polynomial to demonstrate their case. Now the interesting part comes. So we're going to I'm skipping one step. Step 3, of course. It concerns the calibration of parameters. So here they use the sum of squared residuals. You can see that here, equation 8. But they don't use the actual observed and simulated flow, but they use the log transform of the simulated and observed flow, so that the simulation of lower portions of the hydrographs are constrained. And they use a global, so-called global optimization procedure to find the parameter sets that best fit the simulation with observed values according to this criterion. So this is just one number, the average of the sum of squares of the log of observed versus simulated flows. So the interesting part, as I said, I was a little bit too fast, is section 4. Here they recalculate the storage-discharge relationship. So remember that they use the second-order polynomial assumption found in step 2, and then they sort of test after calibration if this is a valid way of representing this reservoir. After all, recharge into the slow reservoir was assumed to be small, but this remains to be tested, as I said. So the authors test this by calculating recession with as well as without consideration of the recharge so far calculated within the model simulation with the optimal set of parameters. Now this is shown in figure 6. I have to go back, unfortunately, to the previous page. Here in figure 6 you can see that in yellow you see the depletion of the slow reservoir without recharge considered, that is the yellow line, and you see the depletion of the slow reservoir with the recharge considered. And you can see that the specific discharge is here plotted on a log scale. I think that is important to mention. So you would expect a linear relationship if the groundwater reservoir would indeed respond in a linear way. It turns out that visually there seems to be a quite large influence of the recharge because the difference between these lines is actually pretty large. So they show the result of a number of iterations that they follow in figure 8. So here in figure 8 they have iterated a number of times to come up with a better approximation of the observations here indicated in the blue line over here. In the blue line, this is the master recession curve, yes. But I think figure 7 is actually more interesting. So here they plot the storage relationship against the specific discharge, and you can actually see that in the first iteration it follows this line, but then if they iterate a number of times they eventually reach these lines, and these lines look very, very much linear to me. And the authors also state that, of course, in the paper. 2 to 3 iterations actually already lead to this result, with a maximum of 10% difference between accumulated recharge between successive iterations. So after 2 or 3 iterations, they actually stop the iteration procedure and they accept a satisfactory relationship between storage and specific discharge from the slow reservoir. Let me see, I think in the next page the authors make a number of statements about some of the peculiarities of the model that they've chosen. I think the most important thing to mention about this is that they want to ensure that they can use this model to validly extract the information about low flows whilst preserving realistic hydrological process conceptualization. And finally, the authors show that as a final step, they recalibrate the parameters that are related to high flow processes. So that is mentioned here in section 5. And then they use, going to the next page, they use a new criterion. It looks very similar to the old criterion with the log of discharge, but now they use the actual discharge values themselves without a log transform. Which basically means that you put more emphasis on high flows. That is also why this objective function is called NHF rather than NLF, which is for low flows. So this ensures that also high flows are simulated accurately while preserving the low flow representation. Now within this step, the authors basically fix the parameters related to the slow flow reservoir. Instead they only focus on these 5 parameters which influence the high flows particularly. So it's sort of a stepped calibration approach they follow. Now then, moving to the results section. I forgot to mention that the recalibration of high flow related parameters improves the simulation of high flows while the representation of low flows and flow recession remains almost unaltered. And so it basically proves, you can see that here also in the values of the objective function after calibration only on the low flows, and then here the high flow calibration, and these are the 2 objective functions they use. You see that the low flow criterion doesn't change significantly from the first part of the experiment to the second part. Now the results section, which is on the next page. Essentially in the whole method sections, they have sort of demonstrated their methods by going through one sub-catchment only. In the results section, they basically expand these results already shown for all 8 catchments. And the interesting thing is that they find a very stable conclusion, namely that the storage-discharge relationship of the slow flow reservoir is quite linear, and that the apparent non-linearities in the recession curve as observed in the flow records can be explained by this recharge component. So moving on to, so I'm keeping this pretty brief because the conclusions are more or less the same for all catchments. There is one exception which I can mention, which is the Petrus catchment. Here they find slightly different relationships, and the reason why this catchment behaves differently from the others may lie, this is a hypothesis of the authors, in the fact that unlike the other catchment, it is not a natural catchment anymore. So there's a lot of urbanized areas in this catchment with artificial drainage and sewerage. Now in the discussion section, the authors first summarize their work, and then they describe that the assumptions that groundwater flow is the only flux during recession periods, this may actually not be the case in many occasions. So they come up with a number of fluxes that could occur in other basins as well, that may alter the allegedly linear storage flux relationships, and a number of these are mentioned. I just have to look a little bit for this. So that is mentioned here on the previous page. Evaporation from the riparian zone, transpiration from deep-rooted vegetation, capillary rise to the vadose zone, groundwater abstractions, groundwater leakage, and recharge from the unsaturated zone. And the final one is the one that they actually find or seem to find in the catchment studied in this paper. Finally, they show a bit further in the text that recharge is in fact their hypothesis of the dominant flux causing apparent nonlinearities in the catchments that they have studied. And they finally hypothesize that the apparent simple relationship found in a very complex heterogeneous medium may be explained by self-organization. They mentioned that here at the bottom of this page. And they also further on mentioned that this could be this could be theorized around the maximum entropy production principle. And these hypotheses at this moment remain to be tested still, and at this moment in 2019 a lot of research is actually being done in this field. The remainder of the discussion actually puts their findings in light of earlier work, and I won't go into too much detail on that now. Now, the conclusion section, the final section of the paper, the most interesting finding that is repeated is that in general, the authors find that a linear reservoir works very well to represent groundwater outflow behavior in Luxembourg catchments. And apparently, you can find in data, you can find non-linear behavior. So the data can suggest to you that this relationship may be non-linear, but this may be caused, in this case at least, in the cases of the catchment they studied, by fluxes going into the slow flow reservoir, or into the groundwater reservoir if you like, during recession periods. And in this case, they suggest that this may be caused by recharge. I hope you enjoyed this paperclip, and please stay posted for more.